Thank you, everyone, and especially to Dr. Ben Inglis for taking the time and giving this very important talk. I'm hoping this is one of the many he would give in the series because I think we can learn a lot from his long, what you call, caring and deep investigations into these issues over time. So just a quick uh, um, bookkeeping announcement before I give Ben's bio. Like like all the previous talks in the series, it'll be interactive. Is okay, right, Ben? Just yeah. Ben is not in a hurry to run away after the 1 hour. I think he planned to stay and discuss to the end of whatever, So please stay if you can and ask your questions. The whole point of the series is to educate. Oh, hold on. Yeah, okay, true. What? Okay, I'm gonna remove that person. Hey, Dr. Gold, are you a researcher? Should I remove you? Just a second. Looks like it's gone. That's good.
My post. I did not delete my post.
Sorry about that. Okay, so yeah, the idea is to raise awareness of the issues, improve education, and basically, hopefully, frame directions for projects for people to pursue or contribute towards common projects, especially if someone is willing to pursue them, right? So don't hesitate to ask questions and stick around and basically unearth and whatnot, right? So without further ado, let me give a quick bio. If most of you already probably know Ben very well, but Dr. Ben Inglis is a principal physicist in the Brain Imaging Center at UC Berkeley, provides support to all neuroscience research on a Siemens 3D Trim Trio MRI scanner, as well as providing scientific input on methods development aimed specifically at the problems presented by various BIC users' research goals. In addition to collaborating on scientific methods, he's responsible for training new users to operate the BIC scanners independently. And he also interacts with users to develop new protocols. He's also the scientific director of the Wheeler Laboratory for Advanced Brain Sciences. So in this role, I seek to develop new clinical applications. He seeks to develop new clinical applications for magnetic resonance and other non-invasive methods in the study of physiology and biochemistry of the brain. So most of you probably know him. He's probably best known from his blog called The Practical fMRI, the nuts and bolts, which he's been writing from 2010. I think it helped a number of people, probably thousands. It helped me. And I'm basically, the point of this talk is to get him to share his thoughts and suggestions and where to go. And yeah, Dr. Inglis, thank you again for taking the time. Please go ahead.
Thanks, Pradeep. So hopefully you can hear me okay. Is that loud enough? Great. And my cursor should be moving occasionally. That's good. So, all right, thanks a lot. Yeah, so this is really the sort of summary of about, 20 years of work at Berkeley. And a lot of this hopefully will be revision for many of you. Hang on a sec, got the slides, here we go. So, so I'm going to go through each of these in turn. So the first two will be revision, hopefully for most of you, maybe 10 or 15 minutes a piece. I'll stop at the end of each of these sections for 1 through 4, and with a few take-home points, and then solicit questions if you have any immediate questions on that particular section. Some of the newer stuff is in sections 3 and 4, especially section 4, and there's a mixture of old information and perhaps some tips that you can take away with you to use today, but also some some sort of calls to action for where I think the field needs to change, either change philosophy or improve on what we have currently, because I think we are actually on a trajectory which is actually going to make things worse before we make things better. So, so I'll highlight a few things there. 5 and 6 I shall zip through. There are a couple of slides each, so I'll just consolidate those and then finish up with a global summary of everything. So what are we talking about? Well, it's basically the idea that we should be able to do something at the front end that makes the data better, so that we don't have to try and fix it in post-processing. That's invariably a difficult thing to do in fMRI. So this is the philosophy, to try to do a good experiment. I'm an experimental scientist, so that's really what I spend my time thinking about. So for spin history effects, let's get straight into this stuff. Will be revision, I'm sure. This is what most people think about for when somebody brings up spin history. It's generally considered to be a sort of a whole brain rigid body phenomenon. And you can see the effects on the right-hand column of moving. This, I think, was a swallow or one single nod, which has a perturbation in the slice direction, which, if you're doing interleaved slicing, produces a Venetian blind type pattern. But if you have descending or contiguous slices, you get one single discontinuity. And that's well understood. We typically, with non-SMS EPI, we would do descending slices to give some improvement in our motion robustness. And that's very often sort of the end of the story for many people. You might look at the temporal signal to noise or the standard deviation. Here are some standard deviation images from 2 short time series. I think they were about 100 volumes each. And you can see the effect. This is actually wiggling your feet. This isn't even head movement. So this is the first lesson, is that you have to think much more globally about movement than just what the head is doing. So fidgeting your feet will actually do a couple of things. It can communicate directly through your spine to your head and cause movement of your skull. But it can also just simply perturb the magnetic field, just like respiration does. So if this is aperiodic, you're going to end up with this aperiodic signal. And again, the interleaved slicing has this much more low frequency pattern, this slice to slice banding, because of the next nearest neighbors being tagged essentially in with an artificial shortening of the repetition time between excitations for a particular slice in space. So there's a first tactic. We can use descending slices and we slightly improve motion robustness. But what else? Thinking, again, much more globally about motion, it's not that not all motion is global. Some motion is local. And this is a well-known phenomenon, but seems to be neglected a lot in modern fMRI experiments. I'll come back to the reasons why, I think, in a minute. But if you imagine in the cartoon, this is from a Gao Lu review paper, which is excellent. It gives the full history of inflow effects pre-fMRI, which was Jeff Dunn's and Jens Fram's work, but also just all of the different ways that inflow has been studied. And it parallels the development of arterial spin labeling methods. So in this cartoon, if the blood is magically turned off, then there's no blood flow, then the spin history is easy to understand, because the blood in the pipe with the dots would relax with its real T1. The tissue assumed stationary, and the slice would relax with its real T1. And in a steady state, everything would be good. But things start to get interesting when flow comes into the picture, because now we have an effective relaxation time which shortens the apparent T1 for spins which are moving out of the plane. And what we actually end up seeing will be a very complicated picture, depending on the direction of the pipe, the thickness of the pipe, the flow, the velocity through the pipe, the slice ordering, the flip angle, the slice thickness, many different factors, most of which we can't easily control, at least not on a global fashion. If we knew one piece of space, we could perhaps control it. But of course, across a whole brain, it's very difficult. But one parameter we do, not exclusively, an arterial phenomenon. So by turning up the flip angle, we're adding a sort of upstream arterial component to our response, whereas the downstream venous dilution model stays essentially the same. Okay, so these are sort of two two phenomena, they go in the same direction for the standard bold dilution model. So you can consider them as useful signals, or you could perhaps consider them as noise. It depends on what you're interested in. I'm particularly interested in hemodynamic lags. So I like to use the flip angle as a button to change the arterial versus venous weighting in the signal. But now what I want to look at is whether there are other consequences from flow that might be producing confounds that we may or may not be interested in. This is the first lesson, is that not all hardware is created equal. If you look at, if you have a head-only coil at 7 Tesla, then you end up introducing a spin history effect, because the blood is sitting outside of the sensitive volume of the transmit coil pretty much at all times until it comes up into the through the neck. Then it has essentially an infinite relaxation. So even in this is an MP2 rage from Jeremy Beaumont, but you'd see the same thing in an MP rage. You see these hotspots in a head-only transmit coil at 7 Tesla. You won't see these in a body transmit at 3T. So this is, even though it's anatomical, it's a lesson that hardware considerations can be really important. And the question I have for you guys, since I don't own a parallel transmit system, is, does that mean that the parallel transmission is also interacting with flow in some interesting way that needs to be considered, so that if you go from, for example, from a trio to a prisma, 3 Tesla, ostensibly the same parameters, do you actually change the flow weighting just by virtue of having parallel transmit? That's a sort of an empirical question that people can look at. So what I want to do now is move to considering the pros and cons of changing the flip angle, because I'm going to make the case that we should be using smaller flip angles than the Ernst angle. And this is work from Peter Bandettini's group from a decade ago. So in this paper, they show that, as expected in these parabolic type curves, the raw image signal to noise scales with the flip angle. So it follows the sine theta dependence exactly as you would expect. And this is with, I think, with full relaxation. But when you look at the temporal signal to noise in the dark flat curves at the bottom, you reach an asymptote very quickly, and it's just a plateau. So you don't get any benefit from having higher flip angles for a time series, for the temporal characteristics, which is generally what you're interested in for fMRI. So now we have to ask the question, well, if there's no net apparent benefit, is there a cost? We should at least look at to see whether there are downsides to having high flip angles. So first of all, let's look and see what this looks like in real data. Unsurprisingly, bright images on the right from a higher flip angle, no surprise there. One refrain that I've heard fairly often about flip angles when we argue over flip angles is, well, I need the anatomical contrast for volume realignment, for motion correction. So if I window the images at the same level, then we reveal the first result, which is that the anatomical content is not substantially different. There's plenty of contrast to work on with the low flip angle condition. So, we don't have a concern that we're losing something if we use a low flip angle. But now we can ask the question, what do we gain from having a low flip angle? And if you look on the right, you'll see, or compare the right to the left, you'll see essentially 3 main differences. The first is that there's a much more speckly pattern in the standard deviation image for a 150 volume time series. And if you look, you see these little punctate dots. These are almost certainly blood vessels. So we have this flow phenomenon, as discussed earlier, which is accentuated with a higher flip angle, right? And you may or may not be interested in that. The next thing is that if you look at the edges, you see a more pronounced edge character in the high flip angle condition. And this is consistent with a bright object when it moves, giving a larger absolute difference between the light and the dark areas in the image. So this would be bad, where this would be an enhancement of motion sensitivity. And then last, if you look at the CSF is pseudo flow, so complicated back and forth motion, but it will also have this apparent T1 effect, so that even though the CSF T1 is, the real T1 is long, the apparent T1 will be much shorter and gives us much more fluctuations, including presumably then in the cortical regions in the sulci. So, so there are some good and bad things here, but overall, we would expect that the low flip angle condition would be better for in the case of motion. So this is where I can pause and take a breath for a first takeaway. My suggestion is to use 10 degrees per second of TR when you're at 3 Tesla. This is what we used to do in the early 2000s when I had a Varian 4 Tesla machine. And somehow over the last 10 or 15 years, the field seems to have moved much more back to the Ernst angle to give the maximum signal to noise per unit time. My argument is that all this does is increase your motion sensitivity, and it doesn't give you anything that you're probably interested in unless you're interested in inflow phenomena. So if you disagree with that statement, if you disagree with the small flip angles, then I would ask you to at least look at why you're using the Ernst angle. Don't just do it for inertia. Understand and justify it to yourself, rather than just using it because you were told to or because that's what you did last time. Look at your slice order. It may be important. With SMS epi, we have less control, but I'll come back to that in a bit. And also, as you're switching platforms, do consider your hardware, especially parallel transmit, as the number of channels increases. It may be an important thing for you to consider. You can't necessarily port the same set of parameters, even at 3 Tesla, from one scanner to another if there are big changes in the hardware. So let me pause for breath here, and I'll solicit any questions on spin history effects. I haven't looked in the chat, Pradeep. Anything there?
No, nothing.
Okay. So shall I carry on?
Oh, well, sincere apologies everyone for the little disruption, but I suggest you utilize this time. Ben is a real expert and probably can help improve the baseline for us all. Don't hesitate.
Yeah, chime in. Hopefully it's all perfectly clear. Awesome. Okay, well then I'll move on, and feel free to come back and interrupt. So let's move on to Nyquist ghosts. Again, we're going to look at sort of global and local phenomena. We're going to try and consider lots of differences, in some of which may be desirable, undesirable, depending on your perspective. So on the left is the K-space that you acquire, and on the right is the K-space after it's been time reversed in alternate lines. So we go back and forth, we zigzag across K-space. So the time is forwards, then backwards, forwards, and backwards. We need to time reverse it before we do the Fourier transform. But if you look down at the bottom right-hand corner of the left-hand panel, this is where we're going to assume we start bottom right K-space and we zoom up to top left or top right. You'll see there's a small delay shown in the grid. This is a mismatch between the sampling, where we're acquiring data, and the portion of the read gradient that we assume is happening. So the read gradients and the digitization can easily mismatch based on gradient delays, just the delay in instruction of telling the gradient to turn on. It can be an effective delay produced by background susceptibility gradients. And of course, that means it varies across the entire image because the shim or the background field varies spatially. So this is, we consider this normally a global phenomenon, but of course we can get local ghosting, which can be worse than the global phenomenon. So this is essentially the reason why the Nyquist ghost exists in the EPI. We can consider the real K-space in yellow as being the sum of an ideal K-space and its Fourier transform plus an error term, which alternates with each zag of the zigzag pattern. And this error term has a spatial a step size in the phasing code direction of 2 delta k, rather than the delta k step size as we go through the real K-space. We know that small things in K-space determine big things in image space because they're reciprocal. So if I double the step size from delta k to 2 delta k, then I halve the field of view. And so what we would see in the ghost image looks like a soccer pitch with goalie areas. This image is aliased, but because it's being actually plotted on an image of full field of view, it appears aliased about the middle, but glued to the ends of the soccer pitch. So that's the error term, and then the real image is on the left. It's the sum of the ideal term plus the Nyquist ghosts. So in general, we try to minimize these delays in order to minimize the energy that goes into the ghost. Okay, hopefully all of that was revision. the nice thing about this is that it's prescriptive. So if we plot the halfway line, then we can easily determine where the ghosts will fall in the image. We can just simply fold it over. We can make predictions based on edge detection, for example. And that allows us to look to see, for example, where the scalp ghosts will fall. So here's a scalp ghost. And these are low. These are typical for a well-shimmed head, but they're not zero. And that's mostly because we have some slight residual off-resonance character because of the scalp fat, even though we're using fat suppression, and just simply because the field is not nearly as homogeneous when we're at the edges of the head, where we go from skull to scalp to air. So there's this susceptibility gradient. But we can just simply plot exactly where we expect the ghosts to fall, and that means we can start to evaluate the standard deviation in these areas and ask the question, does it matter? And I can't tell you whether it matters to you or not, because it depends on your particular brain regions of interest. But what you can do at this point is to determine the variance in these positions and determine if they are too high for your particular experiment. So you can make some sort of QA judgment based on the location of these ghosts. And if you don't like where they fall, you can simply change the tilt or even change the field of view in order to move the ghosts around. You have some degree of control. Now, just like all flow can be positive or negative depending on your perspective. Not all motion is necessarily bad. If you're using naturalistic stimuli, saccading, then eye movement is desirable, but it will have consequences. So hopefully I can play this video. There's somebody in the magnet watching a video, doing some task, I forget, it's been a while. But you see the eyes dancing around, and the vitreous is such a strong signal that it will give relatively strong ghosts. Okay, so now we can look to see, well, where do these ghosts fall? We can predict exactly where they will fall in the image. In this case, they're falling on the cerebellum for this particular slice prescription. That's probably okay. If your slice is a straight axial and your eyes are in the plane with the occipital lobe, that may not be so good, since you don't want high variance in the occipital lobe when you're trying to do a visual task. So again, you have some degree of control over how you tilt the slices, and you want to be able to evaluate the ghosting to see whether it matters to you or not. So again, pause for breath and ask if there are any questions. We have some control. You want to always know where your ghosts are falling, evaluate them if you can. If you have a lot of eye movement, you definitely need to look to see where it falls and how big it is. And if it's a problem, then consider changing the tilt, the field of view, or even pretty drastically the phasing code direction. If you really needed to, you could switch to left-right phasing coding. It would be a big deal, but you could do it if it was crucial to your experiment. So let me pause again, and if there are any questions about ghosting, I'll be glad to take them.
Ben, is there any reason that phase array head coils or SMS would exacerbate this? What's the interaction of those with ghosting versus just birdcage?
So hang on a sec. Pradeep, I'm trying to get Daniel Sheltraw back in. He's been blocked out. So somebody on an iPhone got blocked out. If you could try and.
Right. Yeah, I was concerned that might be.
I'll let you fill that. Sheltraw@berkeley.edu if you want to email him. So John, so thanks for the question. Yes. So SMS. The problem with SMS is that it makes things much more diffuse. When you have without acceleration in plane or slice, then the ghosts are relatively prominent, relatively structured, recognizable. The moment you do any kind of acceleration, SMS or in plane, then you have residual aliasing from the unfolding or the grapple, whatever you're using. And that means that you end up with things that look more like a sort of a starry night. It's much less easy to recognize the specific locations. And they also tend to be much broader, right? So it's harder to do. But you also have two artifact sources to worry about. And I suppose If you're doing SMS with movie watching, then I don't know. I would probably try to evaluate without SMS and just look and see how the ghosts behave on their own, even though the sampling is different, and then turn the SMS on and look to see what varies a lot. Maybe even do a control, an experiment where you have just somebody moving their eyes around randomly a lot with no task, and look just to see where in a standard deviation image where the artifact gets high, where the variance gets high. The problem, of course, is that you have limited control over that. You've done as much as you can with your Nyquist ghost correction and your SMS reconstruction. You kind of you get what you get. You have some degree of control over slice tilt. That's probably as much as you can do. I think I would probably just try to make sure that the eyes were never in the same plane as some tissue of interest, if at all possible. So I would tilt until the signal goes somewhere I don't care about, and then not worry about how high it is.
So it's more about the acceleration factor than the actual number of channels you have in your coil. If you're unfolding there as well, or is that also better?
Hold that question, hold that thought, because
Okay.
you're going to see. So one of the big problems here is that we, especially with something like SMS, you're not changing. It's not like we have SMS off, SMS on, and everything else is static. Generally, when you change SMS, you change the TR, you change the flip angle, you change the coil that you might have selected, right? Reconstruction is different. Everything is changing. So, you never really get an apples to oranges comparison. You get apples to soap or whatever. It's always so different. I don't know. I mean, it's going to be very difficult for us to disentangle some of these effects, I think, without simply doing very well controlled experiments that are probably on phantoms rather than on people. I think it's too messy to do on people. But it's a good question, and I shall hopefully address it in a few slides' time.
Jean, you want to ask the question, or should I read it out? Jean Luke Anton is asking if you tried saturated the signal from the eyes.
I haven't, and you could try that. It'll add time. You could certainly put a sat band on, and that would be cool. Yeah, you might need to do that. It's a good tactic. I should add that to the list. Great, good idea. It'll take you probably 10, 15 milliseconds, maybe not, maybe 5 to 10 milliseconds, because you need a spatial gradient rather than a chemical shift selectivity. So if the gradient is large, the pulse could be short. So yeah, you could do that. Whether you would need to do it once per slice, or whether you could do it once for the whole volume, I'm not sure, but it's worth looking at for sure. Yeah.
Romain, you go ahead, ask the question, if you want to talk. Oh, maybe he can't unmute. Yeah, Romain is asking, okay. Here you show a factor 2 ghosting. Can there be a higher one, like 1 line over 3?
Well, if you no, but not the way that we generate the error terms. You'd have to do a different case-based sampling. It's just the way that because we have a zigzagging case base. Even there are other ways to get similar types of artifact. For example, if you do segmented case base, if you do all the odd then all the even lines, if you do them interleaved, you get one kind of zigzag artifact that will give an n/2 ghost. If you do all the negative and then all the positive gradients and case-based lines and glue them together, then the discontinuity in the middle will give you a 0th order effect. So you can get different appearances, but it's really just the zigzagging motion that is producing the effect. It's to a first approximation, we compensate using phase correction echoes at the beginning of each line of readout. So each slice, each readout. And that's used as a first order correction or 0th order correction for the case space, but it's always going to be a zigzag n/2. You can get other n/4 and whatnot if you segment case space, if you do things that are not single shot.
Daniel, you want to say that comment, or is just a side comment?
It's kind of a side comment, but there's been some interesting work kind of using machine learning to pull out detailed eye tracking from MRI data, which is kind of like the benefit of this artifact. But it's also possible the flip could be doable. So if we can say what signals predict the physical motion of the eyes, there might be normally we don't remove these signals because they're kind of so complex and overlapping. But if we can make a clear model of what the effect is across the whole brain, there might actually be a post hoc way to remove them. Might be a bit idealistic, and it's obviously always better to not get the artifact to begin with. But it might be a path forward for some of these messier artifacts.
Do you know if anyone's done like a resting state correlation, like you just plop a region of interest in the eyes and see what varies in the brain with the eye movement? With lag?
I think there has been some studies. I don't know them offhand. The one I just referenced to does similar stuff, so I suspect that they might reference some of those other papers.
Cool. Yeah, interesting.
Cool. Might have it.
Yeah, certainly. If you might as well exploit it. If it's going to be there, you might as well use it. All right. Any other questions, or shall I move on to first big section? All right. So okay. So reference scans for reconstruction. So this is where we get into acceleration for the first time. Two simple timing schemes. In yellow are the reference data, and then the white is the time series that you actually use in your analysis. But there are a couple of problems we need to think about. The first is we can corrupt the reference data. That obviously is going to be detrimental to the entire subsequent time series. But we also have to worry about the case where even if the reference data are perfect, motion-free, that they can be mismatched with the current volume of epi, the undersampled volume of epi, and that's going to cause a local, a fleeting mismatch or fleeting error, reconstruction error, etc. That could have negative consequences for your experiment. So if we look at the effects of motion, this is an acceleration factor 2 in plane Grapple. The problem here is that if you do two-shot ACS, auto-calibration scans, then the first set of auto-calibration data are acquired in 1 TR, and then the second lot is 1 TR later, so 1 to 2 seconds, depending on your repetition time, and that's sufficient for respiratory changes, head motion changes, etc. So it's very easy to get relatively motion contaminated auto-calibration data in plane. So you see that as a darkening of the temporal signal to noise for the entire time series. If we get perfect ACS or assumed good enough ACS, but there is a mismatch between the calibration data and the current volumes, then we see some interesting phenomena. If you look very carefully, you'll see lots of high frequency information. It looks almost like a susceptibility weighted image. You see all of the edges, the vessels, and the gray-white contrast comes back out as a result of this mismatch phenomenon. There is a drop overall in the temporal signal to noise compared to the case with no motion at all, but it's not as severe as when the auto-calibration data themselves are contaminated. So that's just interesting. It means that we can expect local phenomena that may be difficult to characterize with high frequency information. With SMS, we see somewhat similar, but not quite the same patterns. In the motion, the mismatch condition, where the the single band reference data are motion-free or considered motion-free, then we do see this heightening of the high frequency information. We see a drop of overall temporal signal to noise, like with the in-plane Grapple. There's a drop in the temporal signal to noise if we have motion during the single band reference condition, but it's not nearly as bad as it appears for the Grapple condition. I think this is because we're doing a full case base for each line of for each slice. So in full case base, we move on to the next slice, rather than any sort of partial case base. So what we're really primarily interested in, or primarily being affected by during the single band references, is that spin history effect. It's movement primarily in the slice direction. that's the concern. So if things don't, if there's an effective shortening of the repetition time, that's going to create a big spin history effect. But otherwise, they have fairly similar characteristics. So your first question, I'm sure, will be, well, how do I make it go away? How do I make it more robust? John Polymainy came up with a neat trick a few years ago called Fleet. So in the top row, in our conventional sampling for R2 grappa, we would do the first half of K-space, which is labeled segment A. Then we would move on to the second slice. We would do the first half of K-space for the second slice, move to the third slice, first half of K-space, and so on throughout the time series, then come back all the way around to the first slice, and then we would do slice B, segment B. That's going to be 1 to 2 seconds gap between the two halves of K-space. So the simple trick is to do segment A, then segment B immediately afterwards, and then move on to the next slice, slice 2, then move on to slice 3. Now, the consequence of doing that is that you need a small flip angle, or you're going to get a big spin history effect. So again, this brings back to mind, small flip angles are beneficial. We'll stay near full relaxation if we can. So it's a neat trick, and I think it probably helps a fair amount. It keeps the speed through K-space the same, so you don't get any mismatch between, for example, using gradient echo type auto calibration data and segmented K-space or two-shot ACS for the reconstruction.
Ben,
yes.
Sorry, Sean has a question. Sean, you want to ask? Sean Marat?
Yeah, sorry. I was just wondering what happens when you combine in-plane acceleration with SMS. Are you going to see basically the same effect that you would just with the in-plane, and the SMS doesn't have that much of an effect on it, or is that sort of a question left to the reader?
Yeah, well, so I don't favor using in-plane acceleration with SMS. I don't favor using in-plane acceleration, period, because of the motion sensitivity. I think the costs are very high. I realize that people have to do it for multi-echo especially, but I find that, maybe with Fleet, I haven't tried Fleet myself in any great...
We've had mixed experience using Fleet, and at least on the Siemens product, I think a lot of folks have switched over to using a gradient echo calibration rather than the EPI calibration. I'm not sure. I remember you had some strong feelings about this back in the day.
Well, yeah, I mean, it seems crazy to do a half job, right? I mean, we know that in principle, the K-space speed is different. So, well, experimentally, it's different. So we're going to have, in the perverse case where there's low motion or no motion, you're going to introduce reconstruction artifacts. You're going to have these weird patterns. It seems crazy to me to do that. It's a half fix to me. So, and I think
it's a practical half fix. I have some colleagues at the NIH who I think published a paper in MRM about some of the benefits of doing that.
Yeah,
Talagala and Sarles. But anyways, I can put that in the chat and we can discuss later. I don't want to sidetrack you.
Yeah, thanks. Yeah, good point. Yeah, but in general, as a more general point, I think these artifacts tend to combine and overlap, right? So you have reconstruction artifacts or motion sensitivity from ACS in grappa, and then you add SMS, you get another source of motion sensitivity, and what you get is some really sort of mixed up effects, which are probably hard to disentangle, and it's certainly not going to be better. It may look better because things are smoother and the energy is distributed, but I think things don't generally get better when you consolidate problems. They tend to get worse. So yeah, but we can talk about that at the end maybe. So an idea that Daniel Sheltraw had a long time ago, decade or more ago, was to do something fairly simple to improve the auto calibration scan data for grappa. That's just simply loop on it. This was 10 sets of two-shot data, and so we got odd lines, then even lines, odd lines, even lines times 10, and that gives us 19 pairs of next nearest neighbors. So for odd 1 with even 1 with odd 2, and so on through the time series. And then you simply look to see which is least motion contaminated using the Nyquist ghost correction echoes. You just look at, they are a nice sort of navigator. So you look for the minimum difference between the navigator echoes for all of the pairs in 19 sets. The square boxes depict the best case for each trial, 4 trials in the rows, and the dashed boxes are the worst. So when there's a lot of motion, you see a lot of ghosting. Great, this seems to work quite well. So it's a relatively benign way to improve the motion sensitivity just by simply doing more auto-calibration data and then selecting the best and using that through the time series. I wonder if we shouldn't be doing something similar for SMS as well. We can always loop on the reference data. Generally, scripts don't start. There's no TTLs coming out from the scanner until epi volume number 1. So this is all sort of free time, if you like. It's time we could add robustness to our experiment. One way would be to expand Daniel's scheme. So if we acquire multiple sets of calibration data, we could then perhaps simply select the most appropriate of the reference data for the current volume, rather than just using the best reference data for the entire time series regardless. We could perhaps try to do a more volume-wise match. Of course, this does immediately beg the question, well, how well have we sampled the motion space during the reference data? And if you haven't sampled all of the different head positions that result, that arise during the time series, then you're not necessarily going to help yourself very much. I think this might work quite well, though, for well-controlled head motion, where you're more worried about things like respiratory effects, or apparent head motion effects. This might be a fairly simple way to improve things with a relatively small set of maybe 3, 4, 5 reference data before you start. So I think if I remember rightly, I did request to Eddie Arbach that we add a looping feature for the single band reference data for CMRR's multi-band code. I don't know what the status is, but in any case, the principle is the same as Daniel's. And everything else is already in existence because we can use the navigator echoes, the Nyquist ghost correction echoes as navigators, as motion navigators. So it's a fairly easy thing, I think, for us to implement. All right, so again, pause for breath. My general philosophy is to do what you need, not what you think you should do. So if you don't need acceleration, if your spatial and temporal specification, if your question can be answered with relatively coarse voxels and relatively slow sampling, then don't use acceleration. Only use it if you need to. If you have to use it, then you need to make sure that you've got good tactics to offset at least motion during the reference data. And I think just in general, I find it, things have moved very slowly in this space. I think we could do an awful lot better. I think we've done good enough, and we've just settled on good enough. And I would I'd like to go back and look at all of this so that in answer to questions like Sean's, that we really know that we've uncovered every possible trick and deployed all of these tricks to get maximum robustness. I think we've done a pretty poor job. I think we got happy with what we had, and I don't like that. So cool. Any other questions on acceleration?
So I had the same question actually as Sean about Porsche Fourier and how that plays into this, but I was going to also insert a comment, if I may, real quick, is that I feel like we haven't talked about, or as a field, the just dumb behavioral stuff in the experiment. Like people often have instructions on, and then when they get the first EPI pulse, that's when you change the screen and you go to fixation. And so like when I teach, I always teach before you even have the calibration scans, you go to fixation, you actually emphasize in instructions to subjects, that's the most critical time to hold still. Because I think oftentimes people do the last wiggle, the last swallow, the last little whatever, right in the middle of your reference scan, and then you've tainted your data for that entire run. And at least in my experience, I found that just kind of doing that stupid human thing actually has helped quite a bit.
Yeah, that's a good point. That's a really good point. And I remember, golly, must have been probably 10 years ago now. It feels like the week before last. I remember working with a researcher who wanted to do very high resolution diffusion scans. This is pre-SMS, so the repetition time was very long. And because of the voxel size was so small, he had to have, I think we even used Grapple factor 4 on a 32 channel coil for very heavy for 80 or 100 diffusion direction scan, very, very long. The repetition time was close to double figures. I think it was probably 8, 9, 10 seconds. So you've got, factor 4, you're doing ACS for 40 seconds. A lot of stuff can move. And it was horrendous, unsurprisingly. So we developed these fairly simple tactics. We would train the subjects and we would basically have them do a breath holding task. So they would, full inspiration, and then they would hold, and then they would listen for the slight change in the high frequency information in the scanner, and then they could breathe normally. So we would, and it worked really, really well. It's not something that you can do easily with lots of subjects, but for that particular scan, it worked well. And I think that does illustrate, it's really important that you think about the instructions that you give your subjects, how many true dummy scans you include before you do reference data, and all of this other stuff, and what people do at the beginning of the scan could absolutely be crucial.
So then my actual question was the same as Sean's, is how do we think about these considerations with partial Fourier instead of Grapple?
I haven't thought about this for a long time, probably 5 or 6 years, maybe more. In general, with partial Fourier, you're worried about losing data rather than getting artifactual data. I know things fall off the edge of case base. In fact, I was going to do if I'd had more, I'd be talking for a day. But if I'd done a section on partial Fourier, I was going to have one of those people sailing off the edge of the world, the flat Earth, because that's how I think about partial case base. You're so shim dependent with partial Fourier. In general, I think it works okay. Most people don't use more than like 7/8 for very high resolution for like SMS with EPI to keep the TE reasonable. But my concern is that, if you're doing SMS and you've got partial Fourier to shorten things, and you've also switched to doing a 32 or 64 channel coil, it's hard to even think about the rank ordering of which is the most detrimental in terms of motion sensitivity. If you're going to get motion, it comes back to don't have motion. So I'm not even sure that it's worth worrying about. My bigger concern right now is in the next section. I think we have actually been driving down a road which is going to take us to some bad places without really fully appreciating the costs. So I'm personally not so worried about partial Fourier with SMS versus the SMS itself and the use of large array coils. But certainly at some point we've got to look at that. Maybe there are better ways to speed things up using some other partial Fourier than just the way we do it right now.
Great, thanks.
So just to clarify, Ben has time to stick around and see it through. So if you have time, please stay. If you need to go, no problem. We are recording the thing and we'll be sharing the video later. So
this next section is the big one, and this is I think arguably the most important thing that I think we need to be thinking about as a field. So I'll start with a relatively recent lesson. I saw this experiment depicted in a paper weeks ago. I won't mention any names. It was an anatomical study, but it's a two-time point time series, still a time series, just using anatomical scans. And this is their experimental design. They then went on to claim all kinds of anatomical differences over the 10 or 15 minutes between the two scans. But at no point did they think, or did they talk about in the paper, adjusting the systemic effects that could affect the appearance of the anatomical scan. And at a minimum, over something like a 10-minute gap with high duty cycle sequences like diffusion, or even if you're using foam padding and the foam is compressing, or these are fMRI naive or MRI naive subjects where they're relaxing over time, all of these kinds of chronic effects are going to require a reoptimization of at least these three fields. The shim is obvious. The coil sensitivity map, less obvious, but arguably at least as important. And if you're using parallel transmit, then the parallel transmission probably needs to be tweaked as well. And until you've done that, I don't think you can infer anything anatomical about differences. I just don't believe it. So this is the cautionary tale. It's a simple case, but I want to spend the rest of this section focusing on the coil sensitivity map, because this is, I think, a really important limitation that we're baking into our hardware design. I'm sure you've seen these sorts of pictures before. So what are we talking about? Well, as we go to these larger array coils, the loops get smaller and they still drop off radially. So we end up with lots of little hotspots, which we have to sum together using, let's say, root sum of squares or an adaptive combination. Ultimately, we have to combine all these little tiny signals into a full single image. You can see immediately, and this is just a Siemens bottle, a cylinder, you can see just the pattern of heterogeneity is so strong in the 32 channel coil compared to the 12. And the greater the number of loops, the smaller we make them, the stronger this heterogeneity will become. But why do we do it? Well, because the clever RF coil folks have shown us that you still see a net benefit in overall signal to noise, and that's true. So there's the solid curve for the 32 channel coil, and look, even in the middle, the sum of all the little tiny signals is still greater than the 8 channel or the CP birdcage coil at the bottom. So we overall net, yay, signal to noise up, yay. On the flanks, around the cortical regions, huge gains. But at what price? These gradients are staggeringly steep when you have an array coil. And we need to look at what the costs are, not just the benefits. The first effect, there are two major effects that we need to worry about. The first effect is relatively well controlled, and it's what Daniel Sheltraw refers to as the anchoring effect. It's a nice descriptive effect. And it's simply that when you look at your raw data, on the left is the raw data from the 32 channel coil, you can see the receive bias field imparted in the data. We can normalize that out. And then when we feed the time series into volume realignment for motion correction, the cost function will be driven by the anatomy, that's what we want, rather than being anchored or held back by this lab frame contrast from the receive bias field. So this is an appropriate thing to do. I think everybody now does this. Either they collect pre-scan normalized data directly from the scanner, or they collect a separate bias field map and then use that in post-processing. So this is great. I think everybody does this. It's a standard thing now. The problem is that it's not the only cost. And this is a quote from Larry Wald in a prospective paper that he wrote on the future of high field and large array coils. And he states that even after perfect rigid body alignment, what some people call motion correction, the signal time course in a given brain structure will be modulated by the motion of that structure through the steep sensitivity gradient. So it's these gradients, it's the steepness of the gradient across the brain that is really going to impart a big problem for us, beyond even the motion correction or anchoring effect that I've just shown you. What are we talking about? Well, I can do a simple cartoon to illustrate the problem. This is a transverse view through a perfectly homogeneous receive coil and an object that we're going to make images from. Okay, so it could be a sphere or a cylinder, that doesn't really matter. Then as the object moves around, the images that we collect are identical. There's no receive bias field, so they just move around and there they all are, and it's all beautiful, right? Now we do motion correction on that time series, and there it is, cine looping away. All the edges line up, everything is perfect. With perfect motion correction, nothing is changing. We do a region of interest, completely flat across time. So when the coil is homogeneous and we do motion correction, we recover everything we want. Very, very nice. But now we're going to shift to a real coil, a heterogeneous coil, excuse me, and we'll do the same type of experiment. Hopefully you can see the shading in the pink region. I'm going to move the object around, but as the object moves, the contrast in the object changes too. This is just a cartoon. Don't worry about the specific direction of the gradients. It's just illustrative of the problem. You get a different result depending on where you are in the coil. Okay. Beautiful. Now we do motion correction. And I'm going to click through slowly, and you'll see that although the edges line up, the contrast continues to move around. So that when we do our volume, our region of interest, and we plot that versus time, we don't get everything back. We have essentially stained the data with motion. This is an effect that Daniel Sheldraw refers to as the RFC MoCo effect, the received field contrast motion correction effect. I'm going to change the term to RFC staining because I think it's more descriptive and hopefully it's more memorable. I think anchoring was a really good term for the first problem, and I think staining is a good term for this. And I don't know that anybody even is really aware of it in the field. And yet here we are rushing to bigger and bigger coil arrays, thus making this problem more and more problematic for us. Do you care? Yes, you do. It's a big effect. Daniel ran some simulations. Here's a single 1 millimeter translation in the y-axis for a simulated birdcage coil versus a simulated 12-channel receiver coil. And just for 2 volumes displaced by 1 millimeter, we see percentage difference in signal that rivals even a primary sensory bold experiment, 3 or 4%. It's a big effect. He also ran some simulations later on the 32-channel coil, and you can see up to 5 or 6% shift on the 32-channel coil, which translates, so the bottom, he then ran a simulation using real motion data. So we took the motion data from motion parameters from a volume realignment. We could scale that to change the RMS value and then impart that on a simulated receive field. And you can see that the temporal signal to noise drops from being a minimum of 80 on the left to being mostly below 80 across the image for a 1 millimeter RMS translation. And that's pretty typical. People think that's an acceptable motion threshold for a lot of experiment. 1 millimeter RMS, yeah, good. Well, it's having a massively detrimental effect on your temporal signal to noise. If you go back and look at the original paper that Daniel wrote, this archive paper, he also looked at the correlations that the spurious correlations that this would introduce spatially that could potentially look like, for example, resting state connectivity. So there are other effects than just detrimenting your temporal signal to noise. You're also introducing some spatial temporal correlations in your data that may be distracting to you, maybe cause you to misinterpret something. All right, so let's make it go away because it's a problem. Daniel and I have talked briefly about this and pondered this. It's not trivial to make this go away in post-processing. If you think about, like, for example, the anchoring effect, if we were to do, right now when we do pre-scan normalization, we have one bias field correction. We apply that to the entire time series. If you could get a bias field for each head position, in other words, for each frame in the time series, maybe you would be able to do a per volume correction and eliminate most of the problem. But that would mean you'd have to do a calibration step for each volume, which of course you don't have the time to do. You're already maxed out acquiring the EPI data. You would essentially need the data to fix the data, which is a paradox. So in light of, or in lieu of fixes, maybe clever people can come up with good fixes, Daniel and I shifted instead to trying to avoid the problem. And this is the philosophy that we have adopted as a field to our coil design. We basically use a multi-tool and we just add features to the multi-tool. We assume that the coil, as it gets bigger, still has to do everything, right? Which is kind of crazy. We don't do that in our other tools, but this is sort of become the default for our field. So what about trying to design a sequence and a coil in tandem for the task that you particularly wanted to do? So this was a scale model, a 50% prototype that we worked on with Ken Bradshaw. Ken built the coil. We called it the nested birdcage. It's 3 overlapping birdcage coils. You can see 2 on the outside and 1 underneath in the middle. And this is specifically designed to do optimal SMS EPI with SMS factor 3. So 1 slice per coil, which would be separated with the slice grapper method afterwards. In our original specification, we didn't think about the transverse direction at all, except we wanted it to be homogeneous. The goal is to keep this RFC MoCo or staining effect as small as possible by keeping the coil as homogeneous as possible, but with the one exception, which is the SMS factor. That's what we primarily interested in. But when Ken built the coil, he made it with 2 channels per bird cage. So this is a 6-channel coil. And that just fortuitously gave us the possibility of testing in-plane acceleration for Grapple. The idea being that we would still want to do other images where we want this to be optimal for fMRI, SMS factor 3, and good enough for anatomical scans, diffusion scans, etc., whatever other secondary scans you might have in your protocol. So the 2 channels per coil gave us this option. It was fortuitous. Did it work? Yep, sort of. We got some reasonably nice looking images for prototype. We ran into some issues with magnetic components, which we ran out of time and money before we were able to fix them. But we got reasonable scans, spin echo scans. We got the gradient echo 3D with in-plane acceleration that worked quite nicely. And here are this is a sample I just happened to have laying around in the lab. I put a sea lion head in, post-mortem sea lion head. This was an aborted fetus, which has no gray-white differentiation at all. That's real. But anyway, it was a signal. It was a phantom, and there it is. And we got nice images. So this worked reasonably well for non-SMS. The real question, though, is what did it do with our target sequence, SMS factor 3 EPI? Very small, sorry, but they're just proving that all the slices came back. It was lovely. We had very little residual aliasing from the SMS scheme. It worked very, very nicely in spite of the poor shim. But the important question that we wanted to answer was, would we be able to minimize the anchoring or the staining effect, the RFC MoCo effect? And we were able to. So you can see the distortion here. It's quite phenomenal, the distortion from the shim. Apologies for that. What's important, though, is that the raw data on the left and the pre-scan normalized data on the right are almost identical. There's some differences in the noise, which comes from essentially the masking effect of the normalization routine. But there's very little inherent heterogeneity in the received profile, which will have minimized at source this RFC MoCo effect. We don't even need to do pre-scan normalization for the anchoring effect either. So this really was encouraging. I'm afraid that work sort of came to a halt when we ran out of money. Ken had to go and get a full-time job. He was just a consultant for us. But if anybody's interested in picking this up, I think it would be really a neat thing to look at. And I like the philosophy of just designing a sequence and a coil in tandem. Takeaways, things you can do right now. Always choose the received coil that's sufficiently small, the smallest you can get away with for your pulse sequence. So if you're doing SMS factor 3 or 2, then you might be able to even use a 20-channel coil on a Prisma. Don't automatically assume the 64 channel is going to be better. It won't be. Now, if you have to drive to big SMS factors, yeah, okay, you're going to need to change your hardware, but try to keep the coil as small as possible. Always collect bias fields. If you're doing parallel transmit, you want a parallel transmit correction field too. And always reshim and do update your coil sensitivity maps as often as I would say as possible. Certainly every 10 or 15 minutes if you're driving the scanner hard. If you're expecting motion from foam compression or heating in the scanner, then you should try to re-optimize as often as possible. And I will gladly take any questions on that before we bash through to the last quick section.
So Romain is saying bias field correction is working quite well on post-processing. So maybe bias field correction on each EPI volume would minimize the effect?
Right, the problem is we don't have the information. You need to, so with anchoring, the way that we deal with the anchoring effect is just use a single coil sensitivity map acquired, let's say at the time of acquisition or at the time of your time series or as part of your paradigm, and you can apply that post-processing before you run motion correction. But you use one coil sensitivity map for the entire time series for each volume. The coil sensitivity map with Ribas Deshpande from Siemens when he was in the Bay Area. We figured out just empirically by comparisons, we estimated that the voxel size for the coil sensitivity map is about 6 millimeters. So it's pretty crude. So unless you have very, very, very big movements, then that's probably sampling the received bias field reasonably well for a per volume correction, unless the motions are very, very large. The problem for is that that's only good enough. You know, you're assuming that you have it's a mismatch problem again, just like with the reference information for Grapple or SMS. It's fine as a correction if there's no mismatch. The moment there's a mismatch, your basis set is wrong, and you can't fix it in principle. So it's really about the appropriateness or otherwise of the coil sensitivity maps. And so if when you have a large array coil and you have very, very steep gradients, then that 6 millimeter sampling is not going to be sufficient. You're going to see very, very big effects, and you're going to see all kinds of weird and wonderful effects that you just simply don't correct with pre-scan norm. Pre-scan norm assists with the volume realignment for motion correction, but it does nothing for the intrinsic biases that are baked into your data or stained into your data. Does that make sense?
Yeah, before we go to Daniel, Romain is saying that SPM bias field correction does not use any extra maps. So any comments on
Right.
that?
Yeah, so that's probably because I think that was in part because it was a post hoc fix. I think when they started the Human Connectome project, they didn't have a bias field correction acquired in their protocol, so they had thousands of data sets with no bias field correction possibility. So I think they hacked it out of MP Rage or some anatomical scan, and that's probably fine for relatively crude correction. But ideally you would collect separate maps, and ideally you would collect them more than once. You could consider them like if you were doing a 10-minute time series in EPI, you do a shim, you collect your bias field correction map, tuck that away for one time series. Then you do it again for the next time series, and keep assuming that things are changing, and apply the most appropriate, most current correction map to the time series nearest in time. If you hack it out of an anatomical scan, that's going to be at the beginning of the session. That could be an hour before the current time series. It's probably not, unless you have head cases, it's probably not going to be appropriate to your current head position.
Right, Daniel?
So I think a lot of the multi-echo fMRI studies say that it's pretty good at correcting for these motion artifacts. And I don't think anyone specifically looked into this receiver coil staining issue, but I suspect this is exactly one of the reasons why, because multi-echo effectively is your internal calibration. So it's going to affect each echo, the motion is going to affect each echo in a similar way, but that's clearly not going to be a T2 star signal. So it actually gets pulled out of the data quite well. And if you look at a lot of the motion studies with these high receiver coils with multi-echo, I strongly suspect this is exactly what's happening, and it might be a path forward. That's the optimistic view. The negative view is there's a place I've sort of anecdotally seen this issue arise, which I've seen even less discussion about, which is we do motion correction and we just kind of assume it magically happens, but there's this interpolation step. And we don't tend to do just linear, trilinear interpolation, because it's gonna increase the smoothness of your data unnecessarily. But when we're doing the fancier interpolations, a lot of us do, you're pulling data from further away. And when you're doing interpolation over the steep slope, I've seen some evidence that kind of messes things up. So this is one of these sort of really hard and really complex, but really boring projects that I have not had the time to sort of devote myself to. So I'm throwing this out there on sort of this interaction between these steep gradients and just that simple interpolation step. I think there probably is a solution to that as well, but we have to sort of really empirically designate the problem, identify the problem with that step as well.
Right. Yeah, good points. A couple of other people want to ask questions. I'll comment later, maybe. Yeah, Joe.
Yeah, so this receive coil staining, years ago, I had started noticing how much if you take a parcel average time course from a functional run, even after full pre-processing, it still correlates a lot with the motion if you plot the realignment parameters. So that it is at least partly, we can say, due to this staining effect.
Possibly, yeah, quite possibly. Yeah.
Because I was looking at, I put a post on the blog years ago, and some of you guys in the call commented on it with these pictures. I was trying to remember, and it's been, I haven't looked at this lately at all, but when I plotted areas with the higher correlation and stuff, I was like, this seems like it could, it looks like it could be some of these coil.
Right, it makes sense. I mean, just as a general point, I mean, trying to engineer things out from real brain data is really hard.
Oh yeah.
So, I think we would probably want to drop back and do something systematic. For example, following Dan Hamburger's question on how you, I don't know if it's boring. I mean, it's certainly high reward if you get it right, figure it out. But yeah, we would probably want to do something like all work with the same set of tools. So perhaps we take a real time series. We say this is our pseudo motion, and then we inject that onto either through simulations or movement of a phantom, and then so we sort of have an agreed upon start point. So we're having a language. If we will do different things, we're probably going to make slower progress. So I think trying to emulate this in real data. Daniel did it in simulations. I think the next step would be to take a phantom and drive it mechanically in a way that makes sense, and then look for those correlations. And now we don't have to worry about biology. Oh,
of course. I was more trying to understand what's in the data, as opposed in my data in particular, as opposed to in general.
And as a philosophy, I think you highlighted one of the biggest problems, which is that for example, the nested birdcage project that Daniel and I did with Ken Bradshaw. Why don't people do that more? Well, because the people who develop pulse sequences are in one department. People who develop RF coils in another department. You're an end user, or you're in your interface for the applications, the end user. You're trying to swim upstream where people aren't swimming downstream to you. We've got to get more people looking at this as a problem from the different perspectives. So I think it's just that silo, the way that we work siloed.
Yeah, unfortunately, yeah, I agree.
But it's fixable. I think again, to go back to Dan's point about looking at this, I wouldn't say, again, I think it's high risk, high reward. It's probably something that should be a focus of a working group at OHBM, for example. I mean, ultimately, the entire field depends on this, and you've got to discontinue, even between societies. You can talk about this meaningfully at the ISMRM, go to OHBM, and people are like, what are you talking about? So, there's a discontinuity even at the macro level. I think if the OHBM set I don't know if they have study sections, but if there was a task group dedicated to this problem, what are we doing with our engineering design? Because the specifications, I don't know if Bandettini's on, but Peter will give you chapter and verse on this. He and I have talked about this at length. The driving functions that go into scanner design are not your interests, right? They're not the interests of fMRI community. They're that Swiss Army knife, right? They're clinical. So, they look at this and go, look, fancier pictures, anatomical pictures. That's what sells scanners to radiologists. And if there is a cost, it's incumbent upon us to highlight it and then either circumvent it or fix it. Okay? So we have some agency. Somebody else, I think, had a hand up. I'm not looking at the chat. So,
Jean did. Go ahead, Jean.
Yeah, I don't. First, I want to just say fantastic talk, Ben. I'll probably want to watch your video again and again over time. Always, there are things that I don't know, but about the coil sensitivity issue, I also put a publication in the chat window. So this is some work that you reminded me of that we did several years ago with Simon Graham. Basically, it's a simple concept using the pace motion estimates, apply an sort of affine transformation with translation rotation. So if initially you have a coil sensitivity estimate, and then just kind of scale that based on what part of the brain is now, based on the motion estimates, are further or closer to a specific coil element. I don't know how well that will work if we have a lot of coils, but for low channel,
Cool.
this has been sort of proof of concept.
Cool, awesome, thank you. Yeah, that's great. Yeah, I think that, you know, just having a that's my primary goal today, right? Is let's shine a big light on this problem, and that we can look at the things that the low hanging fruit that might already be out there. It's always nice to be able to use something that's already in your pulse sequence or on the scanner, and if we can do better by just simply understanding the problem in more detail, then yeah, that'd be really awesome. And maybe we have to do multiple steps. Maybe we do something that's better today, and then we move towards an ideal in 5 years' time with scanner design, hardware design, etc.
So, Ben, I have a very high-level question. Most of these sound to me like they could be good candidate for solutions for best practices in fMRI experiment design. Are they, are they, for example, included in the latest COVID-DAS guidelines? Now, maybe that's done for mostly reporting guidelines so far, but I think sounds like these could be kind of compiled into like, how do you do, this is the best way to run an fMRI experiment if possible, if resources and time permit, right? Do you think we can come up with something like that?
Possibly. Well, I haven't looked at COVID-DAS for a while. I've had to propose a COVID-DAC, an acquisition-based COVID-DAS.
Yeah, yeah, exactly. Yeah.
But
I love it.
yeah, I mean, hopefully at some point we can have a roundtable through this forum about education, because I look at this as an education issue primarily, rather than sort of guidelines. And maybe there's not a big difference between them, but
the thing is, some people do like that.
Better. You can avoid most of them. Yeah, right. So.
Right. So I agree. Some people resist the urge to actually make guidelines, but also there is people who need that kind of authoritative suggestion. Just do this, you will be fine, kind of suggestion.
Yeah,
so
right. Okay. But okay. Well, let's just take the first example. Let's work that one. Smallest array coil. Right now. Okay. Yeah. You can make that. That's easy if you're doing non-SMS EPI and you have a Prisma with a 20 and a 64 channel coil. You're using the 20, right? If you're using SMS factor 6 on a Prisma, then you need the 64 channel or the 32 channel coil. But it's in between, right? Now, if you're doing SMS factor 3 or 4, which is common, and except you could rely on the blipped KP to do a lot of the work on the 20 channel coil, and that might end up being better than the 64 channel with the RFC MoCo effect. I don't know, because it would depend very much on your subjects and the amount of head motion that you have, which is another variable, right? Are you using printed head restraint, light bar, etc.? Right? Are you doing pediatrics? Are you doing ADHD? Right? So all of these things are variables that make it messy. And I've only so many hours in the day. My feeling is to try and give people the tools so they can make their own decisions by educating them. So guidelines, I think, yes, they can be useful, but the problem is on the margins. And that's, it's not easy to give people hard and fast answers. I would much rather talk to them for 2 hours and try and bring them up to speed on something so that they can answer the question themselves.
Thank you.
Shall I, since we're running 12, for me, 9 in California, let me quickly bash through the last 3 or 4 slides, 2 slides, I think, and then we can have the round table, since this is super quick, super easy. This one, this is something that I've seen in the literature recently. There's a debate going on between a couple of groups, at least, that printed head coil restraint doesn't work, makes things worse. I spotted that they both had Prisma scanners with 32 channel coils. And a few years ago on my trio, we spotted that the coil was not particularly stable. In my case, I was in the habit of moving the coil all the way to the back for stability. And what that did was put stress on the front connectors. And so I transferred my physical instability to an RF instability. No bueno. So I had Rick Redfern build me a nice widget, a nice shim here, and it absolutely eliminates all motion. It's nice friction fit, so it's even hard to lift the coil out, but there is no way this coil moves left to right, front to back. It's all locked down. It's very nice. It puts the coil exactly where it needs to be and takes the strain off the connectors. On the Prisma, like the Trio, the 32-channel coil is an afterthought. It's not something it doesn't have the same connector. It doesn't plug into the back of the bed like the 20 and the 64-channel coils. It floats reasonably free. You'll see there's a few millimeters gap on the sides, so it can play left to right. And importantly, it's not restrained in the positive z-axis towards you in the head to foot direction. So the assumption is that the sticky pads on the bottom and this friction, or this pushing the coil to the back, are eliminating all of the potential for motion. But if you're using a bite bar, or you're relying on the coil itself as your restraint for the head, because you've coupled the head to the coil, then I think that there might be a nice fulcrum here, and there's a potential for the entire coil assembly to lift up whenever you swallow or nod. So my concern is that the debate in the literature is really arguing over the way that their coil is restrained on the table. So John and I have talked about making a similar kind of widget, a similar shim for the 32-channel coil on the Prisma, and we have some designs in mind. I'll keep you posted on that. I haven't done it yet, but it's coming. And we will try and do it in such a way that you can 3D print it locally, so that everybody can have the same thing. Final category for today is third-party movement, also something that has come up a couple of times for me recently. I do a lot of sea lion work, or was pre-pandemic, and we would periodically get these weird signal dropouts in our diffusion EPI on our sea lion, and we couldn't figure it out. It was always inferior, near the cerebellum, and it seemed to be pseudo-random. We would repeat the same scan, and it would be in different places at different times. It would different B values, and what the hell's going on? Well, I fortuitously sent Blaise Frederick some of my resting state data. He did an ICA analysis and was like, "Hey, Ben, what's this thing here with a period of one per minute? This is the first component in an ICA." And the moment I saw that, I'm like, "Oh, I'm an idiot." It's because we have a tech in the scan room with the animal, and she is instructed to flush the animal with 100% oxygen every minute to keep it from becoming hypercapnic. So there are two effects going on here, and I haven't yet proved which is the dominant one. I suspect most of it's chest motion. So it's the effective movement of the magnetic field across the head from movement of the chest, well known in fMRI. You've seen that before, everybody, I'm sure. But also it begs the question, well, what can we allow the tech to do in the magnet that it potentially could contaminate, especially something like a resting state data? So leaning into the magnet and doing things like that, probably not well advised. So if you're doing any kind of experiment where you have more than one person in the magnet room, in other words, anyone but the subject, then you need to be aware that their movement can have a negative effect on your data through magnetic susceptibility, or if they're leaning into the bore, perhaps loading the transmit coil differently. So pediatrics, anybody, ADHD, anyone where you're monitoring people closely, you need to think about that before assuming that they're not having any negative effect on your data. So anyway, quick summary. Your take homes for the day, then we can have a big round table discussion. Use smaller flip angles. And if you really want to use the Ernst angle, you need to go figure out why you need it. Check where your ghosts fall and make sure that they're not parking on something really important to you. Please try to use acceleration sparingly. Don't try to overspice your experiment because you think that reviewers are going to like, "Oh my goodness, you didn't use SMS factor 4. Reject." No, you should think about your experiment as, can it answer your parameters? Can they answer the question you have? And if you can answer that question with big voxels and slow TR, fine, then you'll have more robustness in your experiment. Along that exact line, don't just spice it up with a big 64 channel coil. Use the simplest coil you can get away with for your pulse sequence. Anything that moves is bad, not just the subject, not just the head, the feet, the coil, everything needs to work in synchrony. And be very careful about third-party movement. At the very least, try to track it if you can't eliminate it. Have people stationary during an acquisition. So, excuse me. As usual, I just stand around drinking coffee while the other people do the work or bring the money. So Daniel did probably 90% of the work that I've shown you today. Rick has a little grotto with elves and magic pixie dust where he makes magic happen. Here's him playing with Yorick, a little printed Yorick. Miguel's also one of my most important colleagues for keeping things working. Ken was our RF engineer. He's unfortunately gone on to do other things. He was a consultant for us, and Mark brought in all the money and allowed us to go off and do whatever we thought was interesting. So probably wondering what on earth we were doing most of the time. So with that, I will gladly take any other questions and we can have a round table.
Thank you so much, Ben. This has been fantastic. I think, like Jean said, I'll probably watch this video again 4 or 5 times to absorb everything. I think there's a lot for me to unpack. So any other questions? Sean, you were able to finally show your video. Go ahead.
Thanks for doing that. I guess we've got to figure out a protocol to make sure that we don't become a graffiti board for the web. That was really wonderful, Ben, and you know, you got a lot of fans out there with your blog, and we look at the frequency of posting, and we sort of hope it'll pick up again. And some of those old posts will get maybe revised or revisited. I'm thinking especially of you talked a lot. Your name got taken in vain when they had a panel discussion on QC here about the user QC versus the site QC, which I thought was just a wonderful, something we should all be doing, and something that is very topical. I do wonder, like, when you say you don't want to do acceleration, I mean, the big thing for us is trying to get our echo time down with straight SMS at 7T. Like, you tell me how I'm going to get my echo time down to 22 milliseconds without.
I can tell you the answer: faster gradients.
Don't do 7T.
Yeah, well, yeah. If you really must go in Christ, John, you're adding all the variables. Let's start with 3T. Let's look at the pros and cons. So the first thing, I'm assuming you're talking about for multi-echo primarily, right?
Well, not only, no, 17, not 17, not necessarily.
Yeah, because the teacher star is so short. So they're kind of the same basic problem. Right. No, I think, again, your boss has been one of the people who has been really questioning, if not opinionated about whether the benefit of having a clinical machine that happens to do fMRI is a good thing or a bad thing, right? It's a good pub discussion. I've often wondered, so there are two things I'd like to fix in concept. If I was just starting again, if we're doing like building a particle accelerator, right? Would I start from where I am? We know that peripheral nerve stimulation is a problem, but the heart is the biggest problem. So, one way to do it is to build an ASO gradient set and then have just huge, massive physical load with a high amount of audio. Or maybe we just eliminate the problem, pick it up with pickup loops, right? If I think about like a suit of armor, like chainmail. Imagine if you go into the magnet and you put on this thing that picks up the extraneous fields and just grounds them. Then you can have a symmetric gradient set. And you just eliminate the problem. It's like sort of active. It's like active shielding, right? It's a version of active shielding, and then you eliminate the problem where you really most don't want it. And then I think, well, okay, but what's the next problem is, especially at 7T, is the modulation of the field with respiration. Well, if I'm going to put this chainmail on, can I do two things at once? Can I engineer this to detect and be a feed forward correction to the field? So I think that's where I would like for us to sort of discuss things, because I think if we can't get the gradients faster, you're always going to be running into some limitation in software. Ultimately, we have to try to fix this in hardware.
I mean, obviously, there are people who are trying to do really nice modeling and design gradients so that you can reduce PNS, and your not too far away from where you are, there's something like that happening in real time.
Right, but there is but real time right now. They're really swapping the gradients this week. This is the second set already, right? I mean,
rumors have been have diffused out to the East Coast as well about some of that. We looked at trying to do like what Hobie Hetherington's try to do active shimming with a respiratory signal. We actually had that in our initial contract for our first 7T, and for a variety of reasons that didn't work out, because that was the hope was there just to use the respiratory bellows as a signal to sort of anticipate to reduce that, but we ended up, I mean, we obviously thought that was a good idea. And what you were saying about the suit, that sounds like an ISMR abstract I've seen. I mean, I think someone may have tried that, but that's a good idea. If we could null it out.
yeah, you bring up the dynamic.
Low T. I'm still going to be searching for that short echo time.
Got to have faster gradients. It's all about gradients. Steve Blackburn told me in the 1990s. It's like, you know, when you're buying a system, you buy the system with the fastest gradient. It's all about gradients, eddy currents, gradients. That's it. Everything is gradients.
Yeah. So if we could just put an insert in, you know, Brian Rep could get some.
Well, but there are other consequences too, right? You know, the ASO gradients are narrow. And so, you know, trying to do fMRI, you know, you're going to give up an awful lot. The vision scientists might be okay to a degree, but there's no space for anything else. It's just all everything constrained. So, you know, you're sort of, to me, it doesn't seem like the right, you know, there ought to be another path for people to look at too, right? And I would like to start with the biggest dumb polarizing device I can find, right? The size of a house, and then like, okay, with the big space, what else can I do with the space? And I'd like to see some other different approaches for the engineering, just like the philosophy with the nested birdcage coil. Maybe there are other ways we could.
Oh, that's a very nice. Yeah, that's really neat. Right. All right, I'll shut up at this point.
Yeah, well, I'll just add on to your dynamic shimming. I did think of doing a section on shimming. I haven't really looked at that much myself. You know, that's a bugbear of a problem, because everything's, you know, intrinsically nonlinear. That's a mess. It's local. I mean, it's not even clear if it's a scanner effect or a local effect, right? Because it's biological as well as scan based. So, you know, even the distinction there blurs. But yeah, I always come back to the same thing, which is you just have to eliminate the motion in the first place, and then reshim to try to combat the heating effects if you can.
So Case Forge is no longer sort of a going concern. So I don't know anybody else who's in that space right now, other than
I don't either. And
the inflatables and what's that the Swiss company that does sort of the inflatable ones. What are they called? They have I mean, it's a fairly nice system. It works fairly well, but you know,
the Pearltech pads.
Pearltech, that's it. Yeah.
I think they're Czech actually.
Yeah, the people who are serious in our group who are trying to do high res, like Renzo, he always uses those.
Cool. Yeah, it's tough. I mean, unfortunately, there are no easy choices, and elimination is very often not possible. You know, I've been debating with a colleague at Berkeley about, you know, she wants to do pediatrics, 100 subjects in a year. I mean, banging out head cases, even if, you know, we have a printer and we can do hard head cases locally, but you know, to get the information to be able to create those is non-trivial. It's a big logistical problem.
Well,